Hello. Yeah. Hello, everyone, and good afternoon and good morning, wherever you are joining. Thanks for joining us. This is the second series of the Binational Seminar on Renewable Energy and Technology between Metropolitan University and UNAM, United Kingdom Center for Mexican Studies. In this series, we will be having two talks. The first one will be by Dr. Kwestekos, which will be presenting soon. And then we have another presenters, two presenters in particular, Dr. Tom Allen and Dr. Oliver Duncan. They'll be presenting from Manchester Met. So our first presenter for today is Professor Kwestekos Hernandez. He's a mechanical engineer from Universidad Autónoma Metropolitana Azcapotzalco unit. He has a master's degree in finance from University of Jalapa, Veracruz, and a PhD in philosophy of engineering from University of Almeria, Spain. He's a professor at the University of Escolar Nacional de Estudio Superior de UNAM Jariculea in the Renewable Energy Engineering Program. He has worked as an engineer on oil platforms in the Fiana wind farm in Spain and as a researcher at the Institute of Electricity and Clean Energy. His scientific production includes more than 40 articles published in high-impact journals. He has directed more than 25 undergraduate and postgraduate theses and has directed several research projects on energy production. His research focuses on the evaluation of renewable energy sources for power generation, mainly for rural communities. He's a member of the National System of Researchers since 2013 and a member of the steering group of the Center for Innovation in Wind Energy, as well as international lecturer. Please welcome our professor as he delivers his talk on microscale modeling and wind resources assessment. As he gives his presentation, please drop off your questions on the YouTube and Facebook. Thank you. Professor, it's your time to present.
Thank you very much, Dr. Bamidel. Hello, thank you. Good morning, Mexico. Good afternoon, United Kingdom. Thank you very much for inviting me to this seminar. I'm very excited. I'm going to share my presentation. Okay, I'm Quetzalcóatl Cruz Hernández Escobedo. I work at the Escuela Nacional de Estudios Superiores Juriquilla of UNAM, and I'm professor in the Renewable Energy Engineering program. Thank you very much for inviting me. Today, I'm going to talk about wind resource assessment and micro-scale modeling, which is my passion, and I have been doing it for 12 years. And I will give a brief explanation of how I do the wind resource assessment. But first, I want to ask, why is wind resource assessment important? For me, it's necessary to optimize resources, maximize the energy produced, and minimize costs. So, as an example, I will talk about how to assess the wind resource and microscale modeling in the state of Querétaro. The state of Querétaro is in central Mexico, and this state is rich in renewable resources, such as solar and wind. But to begin with, I like to establish the difference between air and wind, because there are mistakes when referring to these two concepts. Air is the substance that surrounds us, and when it starts to move due to the difference in temperature and pressure, it is called wind. So this is very important to establish. But wind by itself, it can be considered as a resource. To consider it as a resource, it must be studied from the ground to the atmosphere and back to the ground, because we have several obstacles, several conditions that can be considered for each site studied. This is done considering the topography. Here in the figure is the topography of a site in Querétaro, and this topography is represented by contour lines, as well roughness and climate conditions. And here comes the first problem. Roughness is defined as the objects that are on the topography, and these objects are given a value. But what value to give, for example, to trees? We have trees in here. What value have these trees? Or in this picture, what value we have in this condition without any obstacles? In this picture, we have houses. What values have this roughness? Are there many trees? Are there few? How many are many and how many are few trees? That's why roughness is somewhat subjective. There are tables with value associated to these objects, as you see in this table. But even so, it is difficult to obtain an adequate value. I'm going to tell you an anecdote that happened in Denmark. Several companies and institutes did an experiment. They were all given the same wind resource evaluation project, the same site, but they were not given the roughness values. Each one had to propose their own values of roughness. What was the result? That all the final values of energy production were different because they have all different values of roughness. So roughness is a good object of study. Weather is another important component. Atmospheric pressure, of course, wind speed and wind direction, temperature, and air density. On this last variable depend a lot of things in the evaluation. I'm going to explain it later. The wind is measured with an instrument called anemometer, like this. This is the anemometer, and wind vane. This is the wind vane, which are installed in a tower at different heights. For example, this is the one anemometer and the wind vane at different heights, because it's important to know the condition of wind, not only one height. From this data of the wind speed, a variable distribution is obtaining, which will show two very important factors. This is the variable. This is the distribution of the wind data, and this line, this curve, gray line, this is the variable distribution fit, and the two factors are the scale factor A. This is the scale factor A and the shape factor K. The scale factor A is generally related to the average wind speed, and one of my proposals is to use it for the proper selection of a wind turbine. Because this is the factor A, the scale factor A, comes from the wind, and the power coefficient comes from the wind turbine. So if we compare them, we can select the wind turbine. This is one of my proposals. So this methodology is in study. The shape factor K, as you know, as its name says, the shape factor shows the shape of the function fit. The representative values of K are 3, K equals 2, K less than 2, sorry, and K greater than 2. These are the first parameters that are evaluated to decide if a site is viable for study. We also observe in this left picture, the figure, a wind rose that is divided by sector. This is the sector 1, sector 2, sector 3, 4, until 12. It's very used to determine where the greatest wind intensity comes from. So for example, this direction. This wind rose also serves to establish the possible trajectories of the wake effect of the wind turbine when positioning this wind turbine. For example, if we position in this, see into this direction, the wind turbine, the wake effect will be in this direction. And this is a very useful tool, the wind rose. Air density must be calculated correctly for the good performance of the wind turbine. Usually when we see as a picture, as a figure, the wind power, the power curve of a wind turbine as like this figure, it has been calculated with the standard value of air density. This is the standard value, but it is at level C. That is 1.225 kilograms per cubic meter. Sorry. If we leave that value, we can have problems when we select a wind turbine. Because as you know, the wind turbine must rotate submerged in air. This is the substance. The density depends on the temperature, so you must calculate the correct value to the density to avoid sorry, underestimation or overestimation the power of the wind turbine. Wind shear, another problem, must be calculated and must be considered as it is related to the height. So if height increases, wind increases. But wind shear is used when the measured height is not the same that the wind turbine height. So we have to extrapolate the values of wind to go to the same height of the rotor of the wind turbine. So for example, if we have a wind turbine here, and we have only data at this point, at this height, and we have to go to this height, we have to extrapolate the data to this height. But wind shear is a function of roughness. And I told you that roughness Um, it's a very, very difficult parameter. If wind shear is function of roughness, so we have to take a good roughness. And what I say, if we want to extrapolate the wind, and we have, for example, trees, the roughness value change. And if we have buildings, the roughness and the wind shear will be changed. So roughness and wind shear, we have to consider it very, very good. In this table, we can see wind statistics. In the first column, we see the sectors of the wind rows from 1 to 12, and we can see that the sector 6 is the one with more wind frequency. Sector 5 is the one with more wind frequency. We see that Weibull factors in the power and in the power density column, we see the factors with factor A and factor K, and the power density. But if we see the sector 5, is the more with the more production of power density, is the sector 1. That is why we have to study very good these wind rows. This sector is the one that produces more wind power. We can also see that the units of power density are watts per square meter. That means that if we see the swept area of the wind turbine, this is the swept area. If we see front of the wind turbine when it's rotating, this is the swept area. If we divided this swept area by square meters, this square meter produce 382 watts, because this is a square meter. That is how we can understand the power density. Up to this point, we have seen a general way how a wind resource assessment is made. It's a brief explanation, but now we will see the principle of the microscale modeling with modeling. But first, I want to thank to the researchers of the National Institute of Electricity and Clean Energy, INEL, of Mexico, to letting me use the WAS software. As you see, the topography in the studio is in the site of Querétaro. These areas are the roughness. So in the microscale modeling, we include the topography, that is red lines, the roughness, and the climate values. That is the microscale modeling. We related from the variables to the ground to the atmospheric values. Now we can say that we have the wind resource assessment. Until at this point, we can see the wind resource assessment. Now, I would like to present a tour with wind resource. This is the site, and we can see it on Google Earth. In this video, we can see the distribution of the wind turbines, which is very important because when the wind turbines are placed in the project, we can see if there are some objects there. We can see hills, and the modeling mesh can also be observed if we have houses, roads, any obstacles that can be a problem when we place the wind turbines. So this is what I do. This is a micro scale modeling. Since we I don't know if you see the let me, I think you couldn't see okay, this is again.
All right.
Okay, sorry, I didn't share all my screen, but now you can see. Okay, in this video, you can see the distribution of the wind turbines. This is very important because we can see if we are on a road, houses. As you see, the mesh of the microscale modeling is on the ground on Google Earth, using Google Earth. We can see where we place the wind turbines. And it's very useful for projects. So this is what I do. This is my passion. I'm very happy to share with you this presentation, sorry. And thank you very much to all of you. Thank you very much. I'm very happy to be here. Thank you.
Well, thank you very much, Doctor. Thank you so much for the presentation. That was very inspiring. I think we have some questions already. Before we go into the question, I just want to ask, so could you please just briefly explain to us application of this in real life environment? How do you, how do you apply this in the industry or, yeah?
Yeah, in the industry, the wind resource assessment is very important. It's the first step to decide if a wind farm can be installed. Wind resource assessment can give us the enough information to know is the place can give us energy. So in classes, in my class, I show to my students how to evaluate the wind energy, to propose projects to the industry, government, and to see what if we have power in this site.
This is really excellent, really good. So basically, this can give us the optimal location within a city where you can locate your, the wind turbine that can give you the best power generation, with high efficiency. That's really good. There's a question here. which is, I think, is about the wind shear curve. So it's saying the wind shear curve change when roughness changes. Is that?
Yes, yes. If roughness change, the wind power, the production of wind power change. So roughness is a challenge. There are tables that give us information, but I think a very good value of roughness comes from experience. The new students of wind energy has to be experienced to give a very good value of roughness. This is the problem.
Excellent. All right, thank you. I think we have time only for one more question, and that is really talking about data gathering. I believe your model rely a lot on data. So the question is, do you have enough sensors around to be able to acquire data that will help you get optimal result from your model?
Okay, the data, it's very important. There are standards that establish the records of the data. We can have data from any instrument. The instruments had to be certified. If we don't have certified instruments, we can have a very good model, and the data depends of time. Generally, 2 years of data recorded by 10 minutes, but we need this time to assess the wind power.
Excellent. Thank you very much, Professor Fernandez. We really appreciate you. Thank you so much for your presentation. So we move on to the next speakers now. This will be a double act between Dr. Tom Allen and Dr. Ollie Duncan. They'll be presenting on the development of an additively manufactured prosthetic socket with an aesthetic liner material for protective equipment. Dr. Tom Allen is a senior lecturer in mechanical engineering at Manchester Metropolitan University, where he specializes in sports engineering. As a sports engineer, he's interested in the effect of engineering and technology on sport, especially in terms of performance, participation, and injury risk. Tom enjoys collaborating with academic researchers as well as working with sports brands and other organizations. He's an active member of the International Sports Engineering Association and acts as the editor-in-chief of the Journal of Sports Engineering. Tom is also a board member of the International Society of Snow Sports Safety and a fellow of the Institution of Mechanical Engineers. The second speaker is Dr. Ollie Duncan. He is a lecturer in mechanical engineering at Manchester Metropolitan University. His research in new materials and structures for protective sports equipment include a combination of material and equipment development and analysis. He enjoys collaborating with sports engineers, material scientists, sports brands, and manufacturers of protective equipment. Ollie is a guest editor of a topical collection on sports equipment and materials in applied sciences. Please welcome Dr. Duncan and Dr. Allen. Thank you. And the floor is yours.
Thank you very much for the introduction. Can you see my slides okay?
Okay.
Yes, Okay, brilliant. So I'm Tom. You just heard the introduction about me, and next is going to be Ollie. We're both talking about auxetic materials. So I'm going to talk about a specific project related to a prosthesis liner, which I've been working on, and then Ollie will be talking about auxetic materials in general and how they can be applied to protective equipment. So I'll give you a brief overview of auxetic materials, and then Ollie will go into a little bit more depth. So my presentation is more of a application based. So auxetic materials have a negative Poisson's ratio. This means that when we pull them, they expand sideways or get fatter. That's counterintuitive and opposite to what we'd expect with normal materials. So if you think about an elastic band, when you pull the elastic band gets thinner. When we have an auxetic material, we pull it and it gets wider. We get the opposite effect when we compress it as well. So we compress it and it gets smaller. This can lead to some different enhanced properties, and that's what I'm going to be exploiting and talking about here in this prosthesis liner. So the title of my presentation is Development of an Additively Manufactured Prosthesis Liner with an Auxetic Liner, prosthesis socket with an auxetic liner. So first of all, I'm going to talk about why I'm interested in this. So this quote was taken directly from the Olympic Legacy document, and it's about encouraging the whole population to be more active. So it's more active physically, and that includes young people. We're working on prosthesis liners, which will allow them to exercise more easily, to play with their friends, to engage in fun activities. So the work was funded as part of a StarWorks network, so that's Devices for Dignity. So StarWorks is about bringing together academia, so people like myself, industry, so people which make things in the real world, and then the NHS, so the practitioners, bringing them together to bring around about change for people with prosthesis. So here we go. This is a diagram to show some of the challenges that these young people face. You can imagine all the daily challenges which they may have to face just to go about and do things which we might take for granted. So for the StarWorks network, before we started the project, there were some sandpit days where we could go along and we could find out about the project, and then we could apply for funding, which is what led to the project which I was working on. So being based in Manchester, I went to the one in Salford, and it was a really interesting day. So you can see there's lots of different people who were there. We did lots of brainstorming. We discussed the different things that we had to approach and the challenges that we needed to overcome. And then towards the end of the day, we formed into teams depending on our specific interests. So I formed into a team with people that are interested in materials. And then at the end of the day, they announced the funding that was available and how we would apply. It was quite nice because it forced us to go through this process quite quickly. We put our funding application in. So mine was in collaboration with Loughborough University and the University of Leeds. And we have Blatchford's as well, who's a prosthesis manufacturer. And it was all about developing this 3D printed prosthesis liner. So the whole socket is 3D printed. We're working on this auxetic liner, and it's auxetic here. And the idea is that this can move and conform and adapt to the limb of the person. It should fit and be more breathable. And that's for long-term changes in fit. So when the child grows, but also for changes throughout the day as well. And we were very lucky to have a postdoc working on this, who came up with this really nice CAD model that you can see here. And it's fully parametric. So what we can do is we can adjust different parameters of this liner, such as the wall thickness you see here, and it will change and adjust. We can look at the gradient for it. So this allows us to design it. This is a very basic prototype, which we have here. This goes into the socket because we were focusing on the liner here, and Loughborough were focusing on the socket, and it comes together like this. Partway through the project, we went to a networking event as well, because there's a whole number of different projects, around 10 projects that were funded as part of the StarWorks network, all related to prosthesis and different aspects of that. And we each presented, and when we were presenting, we had this very talented graphic designer who you can see here, and she was sketching, and then we got an illustration or a sketch about our project. And you can see our project's all about materials. How can we make it more comfortable? what can we do? It's about smart materials, characterization. How do we combine hard and soft? And I really like this, you know, carbon fibers, all these words, all these different things which we were using as part of our project, because we had composite materials, so carbon fiber that we were 3D printing on the outside, so plastic reinforced with fibers, and then on the inside we had this flexible liner, which I was focusing on. So we were quite lucky as well that we got some follow-up funding. So we got successful funding as the first part of the network, and then we reapplied and got some more funding. And here you can see Loughborough University testing the socket, because one of the things we did in the first project was basically come up with a proof of concept. And then in the second, it was more about taking that proof of concept and testing it for its structural performance to make sure that it's actually strong enough. So you can see this very nice test rig which we developed. We're testing them to failure. You don't need to worry too much about the details of the results, but essentially we've got load, the amount we're displacing it. We've got different sockets here made from different materials. Some of these are reinforced with fibers, and you can see that we can get away with quite a thin one if it's reinforced with fibers, and then it will go past this pass threshold here for the standard. And then more recently, we applied for some more funding as part of the Redistributed Manufacturing and Healthcare Network, which is all about 3D printing and healthcare. We're very lucky to get some more funding. So the idea here is we're continuing building on our current work. So we've got this parametric CAD model, we've got this initial concept, we're taking it through to this physical prototype, final prototype, and then the main thing we're really doing now is moving up the technology readiness levels. So we're down here at the moment in these sort of lower technology readiness levels, and by the end of this project, we should be moving closer to here. So this is typically where a university would work, and this would be closer to market. We've got different partners who we're working on to do that. And that's where we're up to. So I'd like to thank you for listening, and I'll pass you over to Ollie.
Oh yeah, thanks Sam for that. I'm just gonna. Oh, I think you need to stop sharing, and I'll share my screen and continue.
So while we are waiting for Oliver, please, people, you can be dropping your questions on Facebook or on YouTube channel. Thank you.
Yeah, would you like a pause to ask Tom some questions, or should we do questions at the end?
Question at the end. Questions
okay,
at the
I'll carry
end.
on then. Yeah. All right. Yeah. So if you can all see this now. So yeah, I'm Ollie, and as I've been introduced, I'm a lecturer at my Met in mechanical engineering. So most of my work is around applying new materials to protective equipment, and these include exotic materials, which Tom has given a nice introduction to, and I'm going to continue to talk about now. So I'm going to go through a bit of a background into impact protection and also exotics, and then discuss some of my own work using exotic open cell foam to kind of show the benefits of being exotic, before some more useful and recent work in exotic closed cell foam that's, I think, more useful for sports equipment and also prosthesis and things like that, before wrapping up. So there are kind of two broad types of protective equipment, really. You can either be really well protected, so kind of foam layers covered with stiff plastic shells to spread loads and protect you really well. But this is not always very comfortable, and particularly if you're not on a vehicle powered by an engine, you may want to have more slimline protection, which can sometimes cause kind of cuts and bruises and scrapes. So what we're trying to do is combine both of these things and create slimline protection that also performs really well. One type of material that might be useful for doing that is exotics, which, as Tom nicely described, expand when you stretch them and contract laterally when you compress them. One of the ways this can be achieved is in this kind of reentrant or bow tie-like cell structure down on the bottom right here, whereby the ribs expand outwards in tension and then fall back in on themselves in compression. So this is effectively or similar to the structure that an exotic foam has, whereas a conventional foam has this kind of hexagonal-like structure, And as you see, when it's pulled, it gets thinner. So this biaxial expansion gives rise to their first benefit and their most obvious benefit, which is biaxial expansion. This has been used in various different products, including running shoes that expand with the foot when it hits the ground. Kind of related to this, and still quite easy to visualize, is the domed curvature of exotic materials, which is different to the saddled curvature that conventional materials take on when you bend them. This could be useful for fitting our lumpy body parts, heads, shoulders, knees and toes. And yeah, as you can also tell, both of these are quite simple to visualize and simple to create as well. These are 2D exotics because they are exotic in 2 dimensions. So that's where foam comes in. There are other properties that can be beneficial when you have an exotic material that is exotic in all 3 directions, particularly through its thickness if you're trying to compress it. So you can make an exotic foam by taking a conventional foam, which, as I already discussed, has this hexagonal-like cell structure on the bottom left here, and you compress it. When you compress a foam, the cell walls sometimes buckle, bend, and they take on this kind of contorted or reentrant-like cell structure on the right-hand side. Using many polymer foams, you can then use heat treatment to fix this imparted structure over time. With even compression in each direction, you can create an exotic material that's exotic in all 3 directions. So this process is quite simple to visualize, quite simple to carry out, and it's pretty tunable as well. You can vary the amount of compression, and you can also slightly adapt the polymer by using different heat treatment methods. So it's possible to create a whole wide range of properties, like these ones just here. So we have 3 different types of foam, one that's exotic, one that's got a Poisson's ratio of 0, so if you were to pull it, it wouldn't change its width. The one that's got a positive Poisson's ratio is the conventional foam that these 2 are made out of. These all have fairly similar stiffness as well. So indenting these, as you can see just here, so pushing them with an indenter, the exotic one deforms inwards under the indented area to kind of defend that location. What that does, it means that the energy absorbed by the exotic is higher than either of the other 2. So we now have a material that can resist indentation without a stiff covering shell. This could be useful for making more streamlined and comfortable protective equipment that still works well. But there's a caveat to that, in that exotic open cell foam is generally far too stiff for most protective equipment. Most protective equipment uses closed cell foam, which is about 10 times stiffer. To make exotic closed cell foam, you can't use the same method. Each of these cells are effectively like balloons. So if you compress them in 2 directions while heating them up, the air on the inside expands as you're compressing them and they'll pop. So you end up with ruptured cells. There are ways around this by applying hydrostatic pressure. So that can be either using a pressure vessel to ensure that pressure is entirely even all around the foam sample, or by steam processing, which doesn't require any specialist equipment. So that's what I'm going to talk about just now. We've done a fair bit of work in this over the past couple of years. And here's a demonstration of how the process works. So you take a piece of closed cell foam that's represented by this bottle here, and you steam it. Over time, the steam permeates the closed cell walls and gradually gets absorbed. So this is boiling water being poured into the bottle, which will then give off some steam. The cells are closed, so when you take the foam out of the water and cool it down again, the steam shrinks and it pulls the cell walls inwards, giving a reentrant-like cell structure. Kind of luckily enough, over time, the cells then dry out and you're left with simply a reentrant closed cell foam that then can be exotic. So I can talk through both that and some more exciting work that we've been doing in these, where we've been able to tune the properties in different directions. So we have here a piece of foam in water that's ready to be sealed up and steamed effectively. And then at one end, we have some pins pass through the foam so that when it's taken out of the water and cooled down, it can only shrink in all three directions at this end, and it will be constrained at the other end. So this can be really useful for kind of tailoring foam in different regions to help fit parts of the body and to help protect different parts of the body better. The piece of foam on the left-hand side that didn't have any constraints, you can see that the cell structure goes from hexagonal to, once again, kind of roughly reticulated or reentrant. It's got these kinked cell walls. You actually notice there's a slight shape effect here, and it's because if you start with a sheet of foam, the cells on the outside can't obviously trap steam because they've been cut at some point. Because there are a different number of cells in each direction, but then when during shrinking don't shrink, you get a slightly more compression through the thickness. That shape effect is massively exaggerated by the pins, which mean that there is absolutely no contraction in either planar dimension. So you can see here, if you look from above, where the pins have been constraining the foam, you still have a hexagonal cell shape. Whereas over on the other side, where it's compressed through, this is looking through the thickness, you get this kind of long and thin reentrant-like cell. So looking at the Poisson's ratio of these, remember negative is exotic. You can start by the black line here, the conventional foam, and its Poisson's ratio is roughly even at around about 0.4 or something. Going to the unconstrained section of foam that was able to shrink a bit in all three directions, you can see that the Poisson's ratio is roughly minus 0.4 or 0.5. And then this long and thin reentrant cell gives an exaggerated Poisson's ratio, negative Poisson's ratio of -1. So we're able to create a clear difference between the two regions of foam, one of which would be expected to have a higher indentation resistance than the other, because it has a lower negative Poisson's ratio. Just out of interest as well, all of these foams are of the correct stiffness for use in sporting protective equipment, which happens to be quite similar for other biomedical applications, including footwear and prosthesis and things as well. So the starting foam had a Young's modulus of 1 megapascal, as did the produced exotic foams in compression. So just here I can show you through the different types of gradient foams that we're able to make. So starting with unconverted and then uniform exotic, and then the gradient exotic foam I just showed you, and a much more gradient one over on the right hand side, where steam was actually not able to reach one part of the foam. And you can see conventional foam contracts in tension, exotic expands, indicated by the yellow to red color, and the gradient samples are different at either end. And then finally, we needed to confirm that this behavior is still present at high speeds. So we did some low speed and high speed compression tests of a range of different exotic foams that you can see over here. So you can see that at low speeds, the exotic foam is contracting laterally, and it's doing the same at high speeds as well. So still present at high speeds that would be expected under impact. So now that we've kind of made that and shown that it should be, well, these properties are still present, we would expect under the high strain rates expected during impact, we're going to start applying them to different types of sporting protective equipment, such as footwear, wrist guards, rugby padding, and helmets, for which we have various different projects undergoing with our collaborators and also at ManMet. I mean, yeah. As we kind of continue doing this as well, we're going to look for other applications, which may include also prosthesis and other biomedical applications. So just to kind of wrap all of that up, exotic foams have already shown promise in protective equipment, largely due to their unique shape change and ability to defend an impacted area under impact. Protective equipment typically uses closed cell foam, which we've been developing and working on at the correct stiffnesses for use in such protective equipment, like this one here. And we would like to keep sports participants comfortable and safe by using this type of foam. So yeah, thanks all for listening, and yeah, feel free to ask any questions.
Thank you very much. Thanks, Oliver and Tom. Thanks so much for that. Okay, so I think, yeah, I'll take the first question here, which is, how do you find a balance between costs of material and the functionality of the prosthetic or orthotics? How do you find the balance between the cost and the performance?
I'll take that question if you like, because that was to do with the prosthesis. So our project really at this stage is about a proof of concept. So can we move from the traditional approach, which is where we'd almost be creating a bespoke prosthesis socket for each individual? And it's not so much about the material cost itself; it's about the time of going through that process. Someone has to, make that and do it by hand, maybe. Whereas what we're referring to here is a 3D printing process. And the idea is that orthotic liner will adapt and move and conform to the shape of different individuals. And maybe the overall fit in terms of the design doesn't need to be quite so precise, because we're building that flexibility and functionality into the product itself. If we can achieve that, then we can make lots which are the same that will fit different individuals, and it will adapt and kind of fit them longer over a longer period of time as well. So it's not so much about the individual material costs. The individual costs of the materials are actually quite minor, really. It's more about the whole process and everything which surrounds that.
Yeah. Would you say that we have impacts on how you take some of these materials or the equipment, not just for professional sports people, but also just to average person that wants to use it? Because when the cost comes down, then the public can use them more. Is that?
Yeah, exactly. So even though a lot of the stories from the companies will be around professional athletes using things, it's the everyday consumer that they're trying to sell the products to, and they're the people that benefit. So much of our work, and particularly the work that Ollie's doing at the moment, is around how can we have an efficient mass production process.
And okay, so Ollie, do you want to throw light into that a little bit in terms of taking this from not just professional athletes to the mass populace?
Yeah, and I think Magda had possibly asked a question that's related to this, so we can answer both questions at once here, which is, so there are various different ways to make exetics at lower costs. So most exetics that are already in products use kind of molding methods or cutting methods, and those are the 2D kind of structures generally. There are now 3D exotic structures that are already available as well, and these use slightly more complex molding processes, but still are made via molding. Now, as the cost of 3D printing comes down, there's kind of more and more opportunity to make more bespoke and tailored exotic products, and also more complex geometries. And then we have foam, which is a whole other thing in itself. But essentially, there is at least one company that's mass producing exotic open cell foam. Nobody at the moment seems to be mass producing exotic closed cell foam, and we're working in this area to, rather than using the steam processing method, using a slightly different method and developing it to try and come up with a more viable and mass producible method there. The nice thing there being, if it's possible to develop a method to make exotic closed cell foam, it should still be quite a bit lower cost than say 3D printing.
Okay, so just again, I think to Oliver, would you say aesthetic material works like non-Newtonian fluids?
They're not quite the same. So the exotic property can be present at low and high speeds, whereas non-Newtonian fluids simply increase their stiffness at high speeds. So they have, well, actually, non-Newtonian fluids can do either. So you can have ketchup, which is a shear thinning fluid. If you hit the top of a ketchup bottle, you notice it then falls out the bottom. So the viscosity decreases with shear strain rate. You can have the opposite as well. So those are kind of generally known as shear thickening fluids or something along those lines, or polymers. And they have an exponentially increasing viscosity with the applied rate of shear strain. And that's essentially due to the structure of the polymer and different phases within the polymer as well that kind of catch against each other. It's not quite the same as
All right, thank you.
behavior.
Thanks. Tom, do you want to just throw more light a little bit in your work, what you do with international organizations, sports organizations, and how you relate with them? And yeah, just tell us a bit more.
Yeah, so I've got different organizations that we work with. So I work with World Rugby. So we're looking to review and update the regulations around padded clothing in rugby. Essentially, it's about making sure that we have the player welfare, at the top of the agenda, making sure that the padding is appropriate for their use. So we work directly with World Rugby on that project and collaborate with the manufacturers and the different test houses. And we're working with the University of Sheffield as well. We work with FIFA as well, so another governing body, and a project we have with them, we're looking at how a ball deforms under impact and how the implications that may have for head injury. Then we work with other organizations. I have a PhD student in collaboration with Sheffield Hallam University, works for GB Boxing, and he's looking at wrist injuries and measuring wrist angles for boxers. I work with lots of different companies as well. I have a PhD student who's recently just started a snow sports brand, Rosanol, and we're looking at modeling skis. So lots of different. That was just a few examples.
Yeah. So how thanks, Tom. How does this affect in any way policy development across maybe within the UK or maybe outside?
So it's mainly related to regulations and standards. Yeah. So with World Rugby, for example, we're updating the regulations that dictate what everybody has to use when they play rugby. So when those regulations change, every manufacturer's products will have to conform to those regulations. Every person playing rugby who's wearing padded clothing will have to conform to those regulations. So it's actually quite a big deal already, because it means that because we're working directly with the manufacturer, so with the governing body, essentially sits at the top of the tree. Everyone underneath that has to then conform. And we also work with standards as well, so ISO standards for wrist protectors. And again, if you have a new standard for a product, then all the products have to conform to that standard.
Thank you. Thanks, Tom. It's always very exciting when you see academic work getting out, making impacts on people's life, getting used in standardization and policies. So it's really good. So Oliver, just the last question there will be, what is the impact of extreme weather condition on this material, like aesthetic foam specifically, briefly, because we're running out of time.
So we make our foam. We start with a off-the-shelf foam, and we make our exotic foam from that. That off-the-shelf foam is already used in footwear and things like that, so we wouldn't expect it to be affected any differently by weather than what is already out there, although, as with anything can be affected by weather. So no greater than normal protective equipment, really, possibly.
Thank you. And that's all that we have for today. There are other questions, I believe, for Tom, which you can pick up and maybe answer at some point. Thank everyone for joining us. I think you agree with me, this is really an exciting collaboration between these two institutions, and we believe this is going to carry on. Please join us for the next session, which is in 2 weeks. Until then, from everyone here, we say bye-bye for now, and thank you. Thank you, Oliver, thank you, Tom, and thank you, Professor Kwetera. Thank you. Bye.